This material has been excerpted from the college television course, The Mechanical Universe, and re-edited specifically for use in the high school curriculum. The Mechanical Universe is funded by the Annenberg CPB project, made possible by a grant from the National Science Foundation.
Oscillations can travel through a medium such as air or water without carrying matter along with them. These mechanical disturbances are called waves. Water, light, sound, even pressure. They all travel in waves. In fact, throughout the physical world, waves are one of the most common natural phenomena. And nature isn't the only one who can make waves. People can make waves of their own. This is a human shock wave. Notice how the wave moves from one person to the next, temporarily leaving a space in its wake. This non-recurrent wave front was harmless. This one was not. Eniwetok, 1952. The first hydrogen bomb test. The world at large feels the heat of the first nuclear shock wave in the Cold War. But the phenomenon of spreading waves goes back considerably farther than 1952. It goes back to the very beginning of time, and the universe itself, in fact. The Big Bang. And from the very beginning of it all, a disturbance in one place, natural or otherwise, inevitably causes a reaction in another. And so it goes. When any stable mechanical system is disturbed, nature's response is simple harmonic motion. For a single oscillator, that's as far as it goes. But when oscillators are linked, from one to the next and to the next, a disturbance in one passes on to the next and continues on down the line. This is the essence of a mechanical wave. Sometimes individual mechanical oscillators are easy to discern. In other cases, the wave itself is easier to see than the individual oscillators. Perhaps more surprising, waves propagate not only along the surface of water, but even through the interior of a crystalline solid. But no matter the speed or the medium, water, air, or even a solid, all waves that propagate through any medium are called mechanical waves. Mechanical waves, or impulses, pass through a crystal from atom to atom because each atom is bound to an equilibrium position by electrical forces. When disturbed, they act mechanically, exactly like masses connected by springs. When an impulse moves through a system, no single oscillator goes very far, but the disturbance moves right along. The physics of the mechanical wave can be art as well as science, and it can be enjoyed as both. Musical instruments send continuous waves through the air that can be visualized as well as heard. Masses connected by springs may not look like beautiful music, but the principle is the same. And it can be described using a few handy terms. Each wave has an amplitude, the size of the disturbance, which is preserved as the wave moves along. It also has a definite time for each complete cycle, called the period. The inverse of the period is called the frequency. The tone of music depends on its frequency. The higher the frequency, the higher the tone or pitch of the sound. And the loudness of music depends on the amplitude. Whether it's short and sweet or loud and long, every wave has a definite distance from one compression to the next, called the wavelength. The wavelength equals the period times the speed of the wave. Or in other words, frequency times wavelength equals speed. Lower frequency generates a longer wavelength, but the speed remains the same. All mechanical waves follow the same basic principles. Wherever anything makes waves, harmonic oscillators respond and then spring back. The oscillators are linked in such a way that every cycle of one excites the oscillator beside it. Masses and springs can oscillate along the direction that connects them. These are called longitudinal waves. And they can also be made to wave sideways. These are called transverse waves. Water waves are a combination of longitudinal and transverse wave motions. Each bit of water on the surface moves around in a little circle, each circle slightly offset from the next, all together giving the familiar undulation of the watery surface. As a water wave approaches the shore, It comes into ever-increasing contact with the seabed, where friction slows it down. The closer the surface is to the bottom, the slower the wave. When this happens, the thick part of the wave moves faster than the thin part, spoiling its sine wave form and ultimately causing the wave to break. Whether music to the ears or an assault on the senses, sound waves can be heard but not seen. Waves of sound are generated by something vibrating the air. A vibrating object sets the air next to it into motion, compressing and expanding its density with each vibration. That's why a generated sound wave carries the same frequency as its source. The force that drives a sound wave is due to the change in pressure as the density of air increases or decreases. Around the world, in the most gentle setting or the most violent, countless bits of matter vibrate in unison. And according to the principles of harmonic motion, they create the phenomenon of the mechanical wave.
This material is based upon work supported by the National Science Foundation under grant number SPE 8318420. Any opinions, findings, and conclusions or recommendations expressed in this program are those of the authors and do not necessarily reflect the views of the National Science Foundation.